What's up, scholars? So I was feeling like we didn't leave class off on a good note. Feeling like a lot of us were feeling confused, or maybe a little bit like they had no idea what was going on. So I wanted to go back and do a basic conservation of energy question because, frankly, I started you all off with what I think is maybe too challenging of an example. So let's do this example. This is one that I think we can all feel maybe a little bit more comfortable doing, and then now that you've seen this one, I think it's going to make the one we did in class a little bit more straightforward and easier to understand. I think I threw too much at you all at once. So let's start with a generic roller coaster that I made up. We want to know how fast the folks will be going when they reach the bottom. Let's say that the starting hill is 100 meters high. The final hill, the end point is at 0. So h equals 0. That's the final height. Okay. Now, I do really think that the energy pies are helpful. So the person at the top, they will have all potential energy in the form of gravitational potential energy. And by the time they get to the bottom, all of that potential has been converted into kinetic energy. And then, of course, somewhere in the middle, right around halfway, it's going to be half potential, half kinetic. And what we can do is we can use energy conservation to find the speed at any given height. Here, though, I just want to really go back to basics and make sure we're able to do it for the simplest case. We start up here, we end down here. We've picked the bottom as our reference point of height equals 0. So how do we go about finding the final speed? Like many problems, we've drawn a picture. Let's start with our base equation. When we're doing conservation of energy, our base equation is going to be this one. The mechanical energy of our system is conserved. The initial mechanical that you start with is equal to the final mechanical that you start with. Remember that mechanical energy is a combination of the kinetic and potential energies. So at the beginning, we have a combination of potential and kinetic. We'll do some crossing out in just a moment. The final mechanical energy is just the sum of the kinetic and potentials at the end, just like that. So the reason I wanted to go back to basics is this case is the simplest case, and if we're clever, we can make all cases just like this. I'm not going to go into that right now, though. That's kind of what we talked about today in class, which was a little bit confusing. So let's just do basics. So at the beginning, at the top here, we start with all potential energy because we're not moving. So kinetic energy is equal to 0 at the beginning. That makes this one really straightforward to start with. So 0 kinetic energy in the beginning. And then that potential gets converted between potential kinetic down to all kinetic at the end, which means that at the end there's no potential energy. And we know that because the final height is equal to 0. So we can solve this. The final speed, which is what we're looking for, is hiding in the kinetic energy equation. So let's expand that out. On the left, we start with just gravitational potential energy, which you all remember is mgh naught. H naught here being the initial height, which we'll call 100 meters. The final kinetic is just going to be 1/2 the same mass times velocity final squared. And all we're doing now is solving for final velocity. At this stage, we've done all the physics. We've set up the conservation of energy. We used our understanding of physics to cancel. Now it's just a matter of algebra and plugging in the numbers. So see if you can calculate that final velocity given that we've got a 100-meter tall hill. Okay, the algebra steps. So we're solving for v final. Let's divide both sides by the mass by canceling. So we're left with, I'll go back to red, g h naught equals 1/2 v final square. And now we can solve for v final. So I need to multiply both sides by 2. So 2gh naught equals v final squared. So we get v final equals 2gh naught all under a square root. That is the equation that we're going to be using. Now, if you were paying attention in class today, this should look really familiar. I want to address that in just a moment. But let's actually do the calculation. So the final velocity is the square root of 2 times, let's just use 10 for acceleration due to gravity, and then the initial height is 100 meters. So for final velocity, we get 44.7 meters per second. Just for some context, so you know what that means, I know many of us aren't necessarily comfortable thinking in metric units. If the hill starts at 100 meters, and the final velocity will be 44.7 meters per second. For context, that's a starting hill of about 330 feet, very, very tall, and you end up at almost exactly 100 miles per hour. That is, by the way, completely a coincidence, 100 meters giving us 100 miles per hour. So my hope is that this video has been helpful. We used the same elements that we did in today's video, and the information we went through is just a simpler case. The reason that it's simple is because the final potential energy was 0 and the initial kinetic energy was equal to 0. The next thing I want to address gets a little bit more involved, but I think it will connect the dots between this simple example and the example that we did in the notes today. So I wanted to go back and talk about picking a reference height. Let's say instead of wanting to know the final velocity at the bottom, which we calculated at 44 meters per second, we called this the final height, where the ground is. But it's actually kind of arbitrary, because if you imagine this roller coaster, it's probably on top of cement, which is not, at sea level, and for complicated reasons, sea level isn't 0 potential energy. We'll talk more about that later. What I mean is, you can actually decide where the ground is, or where your 0 height is. Here, if we wanted to know the speed when it gets halfway down, that's actually very easy to do. All we have to do is say, okay, forget the ground. Let's say that this is equal to 0. Let's call this our final height. This will be our initial height. It's sort of like we can just ignore all of this part of the hill. The math doesn't care. The physics doesn't care about the rest of the hill. We're going to say that the initial height is 0. You can show with exactly what we just did that the final velocity at that place is still the square root of 2gh naught, except for that here, this is the part that makes this work, this is now h naught, which is just 50 meters high. So this is like saying we have a hill that's just 50 meters high. We don't actually care that there's a hill below it. We end up with 2 times 10 meters per second squared times 50 meters, and our speed is, when you punch all that in, you get 31.6 meters per second. I wanted to just show you and reinforce this by showing you in the simulation that we used for our lab. Alright, so here is one of the versions of the Energy Skate Park. I'll link this in the email I send out. What we can do is we can move our skater around. So when the skater's on the ground, they have no potential, no kinetic. As we lift them up, you'll see that the amount of potential energy grows, as does their total mechanical energy. It's just a combination of kinetic and potential. Since they're not moving, they've got no speed, the initial kinetic is exactly 0. We've got friction turned off. Now, this is the part I was speaking about just a moment ago. We can change where height is equal to 0, he said in air quotes, by just picking that in a smart way. So if our roller coaster ended here, we would want to make that our 0 height. I'll show you that in just a moment. What you'll notice is that I'm actually physically changing the amount of energy, and the reason I can do that is because energy is kind of made up. So I can do this same activity with a different shaped track to give you an idea of why this is really useful. Let's say, for example, I want to find the speed when it gets to the very bottom of this sort of weird W-shaped hill. If I wanted to know the speed at this moment down here, then I would set that as my height is equal to 0. So if I do that, I'll play it slowly so we can actually see that. I'm going to try to pause it near the end. Boom. Okay. Notice when I get there, my kinetic energy is essentially 0. I'm sorry, my potential energy is essentially 0. That makes doing the calculation that we just did really easy, because the potential energy is set equal to 0 there. But let's say that I wanted to redo this, and where I actually cared about finding the speed was at this hump here. Let's try that. So what I'm going to do is raise this up so that when it gets to this location, the potential energy goes to 0, and I have just kinetic left over. Let's try that. Pause it there, inch it forward. Look at that. Once we get to the bottom here, I've set my reference height in a clever way. Look, we have only kinetic energy. Oh, I need to raise this, lower it just a bit. There we go. So I've set my reference height in a smart location, and we started with potential energy, and when we get to that location, we have only kinetic energy, and it makes, as we described, doing the calculation much, much easier. You could, again, of course, do that same reference height if I wanted to know the speed at this hill. Let's do that. So the potential was some amount. Once we get to the top, look at that. It's all kinetic. Now, of course, again, the total amount of energy has gone down because I've changed the total energy that they had when they started at the top. So that's the game that we can play by picking a smart reference height where we set height equal to 0. Again, the benefit of doing that was that we were able to call that height equal to 0, and when we set up conservation of energy, that means that we can cancel 2 of the terms, and it makes solving much, much easier. So, folks, I hope that that clarification was helpful in some way to you. Please reach out with questions over the next couple of days so that we can make sure we're feeling more comfortable with this kind of information. Thank you so much, scholars.